All right, ladies and gentlemen, this brings us to the last talk that's not a panel for the entire conference. So without any more ado, I leave you in the capable hands of Ahmed, Zaki, and Benjamin Humphrey, who will tell us about selective automated kernel memory differencing, which sounds technical. So, gentlemen, over to you.
Okay, hello everyone. My colleague here is Ahmed Zaki. He's a senior threat researcher at Sophos Labs UK. My name is Benjamin Humphrey, and I am a threat researcher at Sophos Labs UK. And this is Unveiling the Kernel, Rootkit Discovery using Selective Automated Kernel Memory Differencing. So we're basically trying to define a method of automating the discovery and analysis of kernel mode rootkits. So we'll go through the agenda. First, we'll go through the objective and the method, so what we're trying to achieve and how we're going to try and achieve it. We'll go through the system design and implementation. So we'll look at how we're going to run drivers, what kind of data we're going to extract from the kernel, what we're going to do with that data, and then how we're going to report it. And then we'll go through a number of experiments. So we've run a number of high-profile rootkits through the system, see what kind of data we can get back. We've run a number of clean and malicious driver files through the system in order to see if we can attribute any level of maliciousness to specific kernel modifications. And then we've run a random set of PE files through the system and see what data we can get back there. We'll then conclude and start looking at future work. So what are we actually trying to achieve here? Well, we know rootkits are bad, and we know they're pretty hard to find. And our lab gets a lot of samples every day, approximately 300,000. So we need to find some way of weeding out the potential samples that could exhibit any kind of kernel mode behavior. Ideally, we'd like to list the modifications that these samples have actually made to the kernel, and then if we can, identify the maliciousness of these specific modifications. And then it would be quite good if we could import that data into other systems in order to leverage it in some way. So how are we actually going to automate this process? Well, we could use existing tools, but we haven't really found anything out there that specifically looks at rootkits. So we need to build our own system. Now, we could automate this using existing anti-rootkit tools, but there's a number of problems there. For one, we can't control the format of the log files that come out, so lots of different log files, lots of different parsing, that could be a problem. They can be relatively tricky to automate. Not all of them have a nice command line option. But more importantly, we can't control what areas of the kernel they're actually looking at and how they do that. So if some new rootkit technique comes up, we can't modify these applications in order to deal with this new technique. So we've decided to go with our own custom solution. And basically what we're going to do is snapshot specific areas of the kernel, and then we can run our sample through it, snapshot it again, and then we can do a diff and see exactly what modifications have been made. So now you know roughly what we're trying to do and how we want to do it. I'll pass you over to Ahmed, who will explain that in a bit more detail.
Thanks, Ben. Hello? Yeah, so you can hear me. So as Ben mentioned, we wanted a quick way to swift through hundreds of thousands of samples every day and be able to identify in a quick fashion potential rootkit activity. And we didn't want to really reinvent the wheel. So we looked at what dynamic systems were out there that we can use for our purposes and basically design on them or build on them what we want to do. The obvious target was obviously Cuckoo. I'm sure many of you sitting here have used it before and are very familiar with it, but yeah, it's an open source dynamic analysis system written mainly in Python. It's a win for us, highly modular, double win. It's used by, there's a large community behind it, which is awesome for us as well. So we thought, yeah, we're going to use Cuckoo, and we're going to customize it for our purposes. We use, in our tests and in the build of this system, we used an Ubuntu OS as the host OS. The guest VM was Windows 7 x86 SP1 VM in a VirtualBox environment. We had to restrict our system to a maximum of 4 minutes per job, because if we want to go through hundreds of thousands of samples, we really need to be quick, and we need to be able to identify what we want quickly as well. Per sample execution inside the VM, we take around 120 seconds. We start the scanning 105 seconds inside after sample execution. Quickly, bird's eye view, what we're doing here, what modules. I'll speak in Cuckoo terminology, so I'm sure many of you will know what I'm talking about. we built an auxiliary module sitting on the host in order to pull down the internal data that our engine sitting inside the guest VM is going to use in order to dump the essential information that we want. And then inside the guest OS, we'll have an analysis package, basically a Python script to run driver files, because that doesn't by default come with Cuckoo, so we had to write that. And we needed an analysis package in order to baseline the system. Basically give us no operation job. I'm going to talk a bit more about that later. And then we have an auxiliary module sitting inside the guest VM to instrument our Sophos antivirus engine. And on the host OS, we grab that data, we diff it in the processing module, goes through a set of Cuckoo signatures, and finally some nice Django templates to expose this information. Jumping inside the guest VM, we'll have a driver analysis package. Basically, Cuckoo checks the PE header, identifies if it's a native subsystem, then we know it's possibly a driver. Then we use that script inside the guest VM in order to run the driver file. It's very straightforward, really. You use the service control manager in order to create a service. After we create the service, we use anti-load driver by default in order to run the driver. You can specify, so by default, Cuckoo gives you the option to specify options for the analysis package. So the options we exposed in this module were basically the service name. You can specify what service you want to use, what service name you want to use, the start type of the service type, and the load mode here is something, so you can brute force. You can use anti-load driver, and if it doesn't work, try the service control manager to start the service itself. Or you can use one of them, or yeah, that's basically it. Now I'm going to hand you over to Ben. So once we run the sample itself, now it's time to get this information.
Okay, so in order to extract the data from the kernel, we are using our own Sophos antivirus engine. We toyed with the idea of writing our own custom solution for it, but this requires a lot of resources, and we don't have much time, being the busy analysts that we are and stuff like that. So, and with the SAV engine, what we get is this existing presence in the kernel. We get the ability to examine and dump areas of kernel memory, and we also get the ability to write to a log file. So that's everything we need. It's worth noting that this is a kind of modular design. So if at some point we find some limitation with our engine, something we can't access for any reason at all, we could write our own system and we can plug it straight in there. And as long as it spits the data out in the way that we need, everything will work just fine. So what do we actually want to look at? Okay, so the first thing, we want to look at drivers, specifically the driver object. Every rootkit is basically going to begin life as a driver, so this is an obvious one. We want to have a look at the module list, so changes to the module list, whether something's been deleted or maybe it's been added, possibly it's been modified. This could be indicative of a rootkit-like behavior. The SSDT is another obvious one, so have there been any SSDT hooks? Is something trying to hide a file somehow, or is it trying to hide a process? This is good information for us. The IDT, so has a new interrupt been added? To call an interrupt is only 2 bytes, so if you want to save space in your hook, then you may use interrupts. Callbacks is another good one, so this is operating system defined functions, but we've found that rootkit writers like to use callbacks because they can fire an event when a new process has been added, or maybe you've modified the registry or something like that. And finally, we want to look at disk information. So has the MBR changed? Has the partition table changed? Has the VBR changed? In order to find bootkits and stuff like that. So now you know what we want to find. Ahmed's going to tell you what we're going to do with the data.
So once we get this information dumped in JSON format, this gets sent back by the auxiliary module sitting inside the guest VM to the processing module on the host machine. The processing module is then going to be responsible for identifying the base log to use to diff against, our benchmark. When we set up the system, we set it up so that per snapshot you have a specific baseline log. The baseline log gets instantiated by using the analysis package of no operation, as in we don't send a sample inside the guest VM to run. We just run a no operation job, grab all the data that we want, and we tie it to a specific unique identifier per snapshot. So you can have single machine, 6 snapshots, 6 different baselines. This is obviously in order to avoid ASLR noise. So yeah, once this information comes back from the sample analysis log, then we're going to diff it. We identify what's added, what's changed, and what's deleted. We then identified noise heuristically. So we ran a set of files. We found out, for example, that paging out might happen in the process, so we needed to eliminate that noise. We don't want that noise to show up in our diff object. This is in addition, of course, when a snapshot is posed and you resume from it, there's some disk noise that might happen. So we needed to eliminate that as well. Finally, we tag and organize the data according to the sections. So the driver objects, the modules, the IDT, all of this information that Ben was just talking about. So the processing module tags this properly and organizes it, and at the end appends it to the general Cuckoo container that contains all of the analysis log. This is an example of what it looks like. So this is basically part of the SSDT log. So you can see the system calls here. You can see the function VAs. Yeah, they're negative because it's decimals, but it's all dealt in hex at the end. So yeah, you can see the function VAs, the first 8 bytes of each system call. This is in order for us to identify inline hooks. This is an example of a baseline log for a certain snapshot. So you can see the function VA here and the start bytes. Yeah, that works. The function VA and the start bytes. And then here you can see in the analysis log, there's obviously a table hook because the function VA is different. This is what the processing module spits out after the differencing. So you can see here the difference in the VAs, the difference in the bytes tied per key, which is the key here is the name of the system call. Right, so the processing module produces all this information. This goes through a set of signatures, I mean here Cuckoo signatures, that run against all this information in order to highlight what's interesting to us, flag it up, and then finally, as per standard Cuckoo process, you go through a set of reports that bubble up this information. So what signatures did we write? New driver objects, modified driver objects, deleted driver objects, same for modules. New device objects created, and we also have a signature for device objects associated with the service. So in case you submitted a driver file for analysis and you know the name of the service that you wanted to give that specific driver, we will look for device objects created for that specific service. New registered callbacks, modified callbacks, SSDT hooks and IDT hooks, and finally some disk information. So if the master boot record was modified, we will flag that up. If the volume boot record was modified, we'll flag that up. And a signature for the end of disk size. This means the slack space between the end of the file system and the disk. So we know the last sector for the file system, and we know the last sector of disk. In some case, rootkits will hide their file system in that slack space, so we need to identify if that was the case. So this is an example of the reports that we get, the nice Django templates that we added to Cuckoo. This is the kernel memory changes, this coding. So for example, here we submitted the driver file. This was the name of the service we gave. You can see here the new module, the new image base, the size. And we can see that this specific, we dump here the whole driver objects to all the IRPs or the VAs, the device list, all the parameters of the driver object structure. And we can see that in this case, this driver hooked anti-set value key. Then we show all of the different parts of the log. So the sample analysis log, we exposed all that information. So we expose all the drivers, and for each driver, you can see here all the IRPs. You can see some of the fields of the driver object structure, not all of them, but all of them are present in the log, so you can write really signatures on them. This is just for showing, what we thought was interesting. Then you have the modules, the SSDT, the callbacks, whatever callbacks are registered, The MBR, it's not really MBR, it's more than that. It's the partition table, so we really show the partition table and the SHA for each VBR. In this case, we had 2 partitions, the active one we can show you. And yeah, we had the LBA for the last sector of disk and the LBA of the last sector of the file system. And the IDT for each CPU. So that's all nice and sweet, but is this going to work? We really need to see if that's going to make any sense. Is this system going to be helpful for our own purpose? What was our design goal? Our design goal was that we need to find out if a sample is potentially a rootkit. It's not an exhaustive system for rootkit analysis. This is not what we had in mind. So what we did, we had 3 sets of tests. The first set was against some high-profile rootkits, so rootkits that you all heard of, or most of you heard of. So we grabbed TDL, gaps, Turla, and Neckers, and we know what the research out there, from our analysis, what we should be seeing compared to what we saw from our system, and we see the difference. And a set of malicious and clean driver files, and a set of randomly selected malicious executables. So TDL, I'm sure many of you are available know what TDL is. TDL has been out there since late 2010. There are many derivatives. There have been many knockoffs of it. We basically wanted to test if we were going to capture the MBR change. Are we going to see the difference when that happens? And what else are we going to see? Standard classic TDL4 will hook driver start IO of the miniport driver. It will override the MBR, and it will steal one of the device objects associated with the miniport driver. Are we going to see this here? We got the MBR change, but we did not get the driver start IO hook, and we didn't get the device object change. What we got instead was a change in the file system driver, which means, so we got the file system filter manager, the signature hit on both 2 driver objects, and we got a device object added. In this case, this was the address of the device object, and this is the type of the device. If you have a closer look, we can see that this device object was the same device object that was added to file system row. So the device list of file system row includes the devices of file system filter manager. So we can see in this case the same VA for that same device object, which means probably this was a mini filter installed in order to filter out I/O request packets to the file system itself. It's not exactly the same TDL classic version that everyone knows about. The second test was with gaps. So there were, if you were watching Eugene and Alex yesterday, were talking about there are 2 variants of gaps. There's the MBR modifier one, and there's the one that modifies the hidden sectors D word in the bias parameter block. This is the one that modifies the hidden sectors of the bias parameter block in the VBR. So we want to see if we're going to capture that. In addition to that change, we know that gaps normally introduces some kernel sections or code sections inside the kernel, not a full PE in kernel when it loads, and but it instantiates that by first hijacking the boot process, which is exactly what it's doing by modifying the hidden sectors D word. We got that, and this is the example of what noise, for example, we left in the system. So sometimes system calls will be paged in during a job. We will keep that in case we encounter a sample, for example, that will want to page in a certain system call and hook it. So we want to keep that information, but we label it as paged in. We know that this was paged in before because we can compare it against the baseline. Now I'm going to pass you over to Ben, who's going to talk about Turla and Neckers and the malicious and clean driver set.
Okay, so Turtle, also known as Snake, and Ouroboros. This was blogged by GData in March earlier this year, but it's been around for a couple of years now. So from research, we know that it installs an interrupt. We know it has a hidden encrypted file system on the disk, and we know it hooks a number of SSDT functions with this interrupt. So running it through our system, what do we see? Okay, so we see a driver's been loaded, kernel module's been added, we see device objects been added, we see SSDT function has been hooked, and we also see that the IDT has been modified. So looking at this a bit further, so we see the SSDT functions here that have been hooked. We can get the start bytes of those, and if we disassemble them, we see we've got a push, and then we have an interrupt. This is interrupt C3. And if we have a look at the IDT modifications, lo and behold, we have C3. And if we were to take this VA here, we would see that it lies within the kernel module that's been added, so we can directly attribute this interrupt to the driver that's been added. The next one is Neckers. So this has been around since about 2011. It was packaged with fake AV and has more recently been packaged with Zeus. It's got usual rootkit behaviour, so it installs a driver, it creates a service. The driver hides the service and the driver file on the disk, and it also controls what applications are loaded. So running it through our system, we see a driver has been loaded, we see a driver object's been modified, and we see a callback's been added. Now, if we look at the driver that's been loaded, we see we have a name, but we do not have a path, and we do not have a SHA. And the reason for this is that our system can't access the file on disk, and the most likely reason for that is because it's been hidden. Now, if we look at the modifications, so we see a device has been added to the file system filter manager, and we also see we've got a load image notify callback. So the load image notify callback will control what applications are loaded, and in both cases, we can attribute this driver name to the driver that's been loaded. Now, in all four of these examples, what we can take away from this is that we're not always getting enough information to classify specific families. So with TDL, we only get the MBR modification, but we don't get anything else. But what we are getting is enough information to warrant further investigation by a researcher. So looking at the next experiment, we took a number of clean drivers and a number of malicious drivers, about 3,000 in total, and we put them through our system to see what kind of changes they've made, see if we can, kind of identify which modifications are more likely to be malicious. Now, we found that 50% of the clean drivers did not return any kernel data, whereas only about 18% of the malicious drivers did not return kernel data. Now, this tells us, in a roundabout way, that just because something returns kernel data, there's a slightly higher chance that it's actually going to be malicious. Now, looking at the results of this, so new drivers, this is neither clean nor malicious. Everything's going to create this new driver. The modified driver, we're seeing that this is more of a malicious trait than a clean trait. New module, once again, exactly the same as new driver. That's to be expected. The next one was a little bit of a surprise to us. So SSDT hooks, we found that more clean samples hook the SSDT than malicious ones, which was a bit strange. So after drilling into this a bit more, we realized that we've got a lot of security software in our clean set, and security software would like to monitor the system in some way. So that's kind of why that happened. New callbacks, we're seeing that this is normally abused more by malicious drivers than clean, as with the generic attached device. So this is new devices that have attached themselves to other driver objects. But the modified MBR, the generic new device link. So this is where our new driver has created a new device. This is kind of neither clean nor malicious. So what we can take from this is, yes, we can say that a certain modification is more malicious than others, but we can't directly attribute definite maliciousness to any single one of them. Now I'll pass you over to Ahmed, who will go through the last bit and wrap up the talk.
So Ben was just talking about the set of clean and malicious driver files that we looked at. The intention of this system was to flag out potential interesting samples for us. We wanted a quick way to look at this, to identify such samples. This is an example of such case. So in this case, this is a driver that didn't create a driver object, didn't create a new module, yet it installed two callbacks. So we have here a callback on create process notify, a callback on load image notify, with an unknown driver, unknown file path, unknown module. Interesting. We also got two SSDT hooks. You can see that those were inline hooks. You can obviously see the E9 there. an anti-enumerate key, standard stuff. Interesting anti-flush instruction cache. This is exactly what our system, or what we want our system to flag up to us, so that we can go further and investigate what is the sample, what is it doing. Now, we look at the set of PE files that we ran against. Good news is that we really got 96% success rate, as in the 4 minutes was more than enough to get a 96% success rate. This is good news for us, because we don't want to exceed 4 minutes in our cluster. That's the maximum time that we want to give per sample. Well, the other news was that we got less than 5% kernel memory changes. Most of the samples returned the same. They didn't induce any changes in kernel memory. Nothing happened. This could be for a wide variety of reasons. It could be anti-sandboxing. It could be that the sample doesn't do anything. It could be that because it doesn't really do any kernel memory modifications. But the interesting thing from here is that the highest hit was in modified driver objects. This was the highest hit. We got almost equivalent hits in new driver objects created and new modules, less hits in SSDT and IDT hooks, and lower hits or low hits in attached device objects. The idea here is basically what we're seeing is that there's a higher chance that a malicious author of a rootkit will not go and hook, your traditional SSDT, IDT, whatnot. He or she will go for the modified or driver object, because it's much more difficult for a researcher to enumerate each and every driver object and find out what has been hooked. So it's easier to hide in there. Putting this all together, we didn't obviously get hits on all of our signatures, but we used our own experience in addition to the stats that you just saw earlier. So we classified, for example, the creation of new driver objects or new modules as info level signatures. This is, by the way, standard Cuckoo level severity. So in Cuckoo, it gives you the ability to rank signatures as per 1 being less malicious, that blue label, and then you have your yellow suspicious activity and malicious stuff as 3. So yeah, and then we classified as suspicious the modification of a driver object and modification of a module. Standard SSDT and IDT hooks is suspicious. You can see sometimes clean drivers doing this, actually. A lot of security drivers will do this. The registration of a callback, attaching a device, this is all suspicious. More likely to be malicious than clean is the modification of an MBR, obviously the VBR, and the end of disk size. So, in conclusion, what did we get out of all of this? What was the outcome of all of this? What we can definitely tell is that malicious activity can be identified via modifications rather than creation, i.e., the creation of a driver object or a device object isn't per se suspicious, but the modification of a driver object is likely to be an indication of malicious activity more than anything else, more than it's likely to be a clean driver doing this. The second conclusion was that malicious drivers are unlikely to employ anti-sandboxing techniques. This is evident from the fact that we got quite a high rate of replication, successful replication in driver files compared to our PE files. In many cases, the dropper will be doing the job of detecting the VM or the sandbox, etc., and the driver wouldn't be doing this in many cases. Last but not least, we found out that actually our system is not so bad in terms of flagging up interesting samples for us. It can run quick. It will give us good information on potential malicious activity and allow us to go and dig further. Finally, obviously, this is far from done work. I mean, we're still working on this, and we're still going to continue working on it. One of the things that we're looking at dumping more information. So the kernel objects table, I'm going to start diffing that. We're going to look at DCOM as well and 64-bit drivers, because at the moment we only look at 32-bit drivers. We're also going to look at sample clustering, more intelligent signatures. Since we're running Cuckoo signatures, really, we can use information from several places. So we can use, for example, the kernel memory changes in addition to network activity, in addition to user mode activity, and put that all together into more intelligent clustering. And finally, yeah, user mode rootkits, your traditional IAT, DLL injection stuff. And that is really it. Thank you all very much. Questions?